Hello everyone, welcome to the lecture 23. In this lecture, we're going to talk about the stress distribution. So far, when we talk about the stress increment by the superstructure, total stress increment, we've assumed the one-dimensional load distribution. So if this is the ground surface, and we have a total stress increment by delta Q at the surface, at the location A and location B, the stress increment here at sigma delta sigma V, the vertical stress increase, this pen, A is the same as the delta Q. And at deeper depths also, it will be the same with the total stress increment at the ground surface. So stress increment was constant over the depths. Actually, this case is the same with this one-dimensional confinement case. So you have a container, let's assume. In a cup, you have a soil. And when you apply, so you have a loading plate. The size the same with the container size, the width. And when you apply the delta Q, then the stress increment at here, at the shallow depths and the deep depths is the same, because the no lateral deformation is allowed. So in this case, all the force by this delta Q is transmitted vertically. Right? So the soil here will feel the same stress increase with the soil here. And this is called a one-dimensional stress distribution. And this is applicable when the width of the loaded area is significantly larger than the thickness of the compressible layer. So for example, you are building a very large factory. Right? Maybe 100 meter by 100. And the clay thickness is only like 2 meters. So then width of the loaded area is much larger than the thickness of the clay. So in this case, here and here and here, the clay, the effective stress increase or the total stress increase by this, by this loading will stay constant over the depth. But in practice, the load is over a confined area. So we can think of, what is this one? This is the ground surface. And you have foundation with the confined, sitting on a confined area. And then this is the clay layer, which is compressible. Then you have stress increase, Q naught, and here at point A, with depth, maybe we can say the point A, point B, point C. The vertical stress increase at A and delta sigma E and delta sigma C, they They are not same. Huh? They are not the same. It will be different. Huh? And then will it increase or decrease over the depth? It's gonna decrease with the depth. Huh? So the main mechanism can be explained with this comparison. So you have container with a certain width, and the loading area is the same with that container. So in this case, the stress here and the stress is the same. Eh? And now you have the loading plate that has much smaller area than the container. So then if this is the A, then the force will be delta Q over A. Maybe this could be the delta F. Huh? And here the force will be preserved over the depth, huh? Here and here. So then area increases. So area increases as you go deeper. So then the stress, the delta Q or the delta sigma here, the F is delta sigma times area. Right? And then this will go down. Huh? So at the surface, you have a Q. It's different color. That's the Q naught, which is the total stress increase. And with the depth, it's going to decrease like this. Because the stress attenuates with depth. So this is why this 3D analysis is required. And for that, we use the theory of elasticity. So we assume the elastic medium, and we analyze the stress decrease or the stress attenuation with depth. In practical purpose, in many geotechnical engineering design, we design the shallow foundations. And shallow foundations have a confined area, right, for the loading. So you can think of this kind of rectangular area, a square, right? Or it could be a strip footing. Then we will know the geometry of this footing. Then underneath this footing, the wall with the stress at 1 meter deep, or 2 meter deep, or 3 meter deep. And from that, if we know the stress increment, total stress increment at 1 meter deep, or 2 meter deep, and using this, we can compute the settlement, ultimate settlement. Okay? So then that starts the another consolidation settlement estimation procedure. Okay, then how do we estimate the stress increase at a certain depth? It starts from the Pushiness theory. Yeah? And this Pushiness theory is derived based on the elasticity. And the condition is this: you have a point load. The amount of the force applied is Q. So the force Q is applied at a certain point on the ground surface and soil surface. And then the stress increased at a certain location, which is at the depth of Z, and it's apart by the radial distance R. Then sigma Z at this location can be computed using this equation. So Q time 3z cubed over 2 pi r squared plus z squared to the 5 over 2. And if we manipulate the equation so that now the Q is divided by the z square, so depth square, so that this becomes a stress. And then this becomes the influence factor. And it's called the NB. And influence factor is a function of R over Z, right? And the rest of them is just a constant. So then this equation becomes Q over Z squared and NB. And this NB, when you plot this one with the R over Z, it decreases like this. So at the when the R is 0 here, the NB is 0.48 and R is 0, or R over Z is 0. And as the R increases or R over Z increases, the NB decreases. And if the R is 0, the stress increase sigma Z will decrease inversely proportional to the Z square. Then, okay, one more thing to note is that when you look at the stress increase, it's function of Q and the R and Z, which is geometric parameter. So it's not dependent on material property. So it's not affected by the soil property, whether it's clay or the sand, whether its density is very high or the low, or the loose soil or the dense soil, it doesn't matter. The stress will be just determined by the geometry and the force, the point load, because it's based on the elasticity. So because it assumes the material is elastic material. Okay. So then because this is the point load equation, so from the point load, if you integrate, this becomes the line load, right? And if you integrate one more time, this becomes the load over one area. Okay? So integration. Another integration here. Then you will get this Newmark solution. And Newmark solution allow you to compute and calculate the stress below the corner of a rectangular area. So here, if you know the loaded area, the geometry of the loaded area, which has the width of X and the length of Y, and then if you know the Q, which is the stress applied on this loaded area, then you can identify the stress increase at the corner, below the corner of a rectangular area. And here, if the depth of interest is the Z, then you derive the M, which is X over Z, and the N, Y over Z, and then you can identify the M, which is function of M and N. So here I is the influence factor and has the definition of this one. And this influence factor I is function of M and N. So you can solve this equation using the calculator for a given M and N, or you can use this graphical solution or the chart to find out. So here, if you know the N and if you know the M, right, for different M, then you can, for example, if the N is 1 and if the M is 0.1, then influence factor will be 0.02, maybe 0.026, something like that. Okay. So then what about, then this Newmark solution will allow us to calculate the stress below the corner of the rectangular area. So when we think about here, then it's gonna be the below the corner of this rectangular, the scratch paper, right, at here. Then how can we determine the stress increase under the center of the rectangular loaded area? Then here we use the additive rule. So we can divide whole rectangular area into 4 squares or 4 rectangles, and then we look at only here. So this will be the x, and this will be the y, and at the center of, under the center you have a depth z, right? Then m will be x over z, n will be y over z. Then you get the I for the rectangle A, B, C, D. Right? So then the stress increase at the below the center of the rectangular area will be Q naught times A, B, C, D. But because we have now the 4 rectangles, we have to multiply 4. Okay, good. And then the last one is I would like to share and explain the concept of the pre-compression. So pre-compression is when the soil or the clay layer, compressible soil layer is highly compressible, pre-compress the soil to minimize the post-construction settlement. So this is, for example, you have a clay layer at the top, and you're gonna build some structure, right? And we have the delta sigma that's determined by the size of the structure. Then we know that this delta sigma will cause some amount of the SC. Right? So then before doing that, we can just dump the dead weight. Maybe we can just apply some fill that's made of maybe just the soil or the earth material, or it could be just concrete, or it could be water, and it will apply the same amount of the delta sigma, or maybe a little bit less than that, maybe 90% of the delta sigma, apply it, and then we wait until it settles down, and then we can remove it, and then we can start building the actual structure. So the reason is that by doing the pre-compression, the void ratio or the settlement will occur to a certain point, and then when we remove it, because the pre-consolidation stress now becomes here, it's gonna bounce back to the lower void ratio, right? So then when we actually build the structure, it's gonna be here. So you have only this much of the void ratio settlement instead of this much, right? And that's the concept of the pre-compression. So you apply the certain dead load and wait until it settles down, and then you remove the dead load and then build the real structure that you designed before. And it's also called the surcharge loading. Okay, and then in the next page it shows some example. Okay, here we have a 3 meter by 4 meter rectangular footing. It's loaded uniformly by 100 kilopascal. So this will be Q naught, right? And here is the loaded area. Then X is 3 meter and Y is 4 meter. And find the vertical stress increment sigma z by the loading under the corner of the footing at the depth z 2 meter. So that's 2 meter. So we are looking at here what will be the stress increase, the vertical stress increase by this Q naught. Then M will be 3 over 2, so 1.5. And N is 4 over 2, that's 2. So then we can go back to this chart. and 3 over 2, 1.5, n is 2, here n is 2, here 1.6 is here, and 1.4 is here, so it's gonna be in between this, somewhere here, right? So I will say 0.223 maybe, so I will be 0.223, so in this case 100 times 0.223, that's 22.3 kilopascal. So under the corner 2 meter dips, 2 meter deep, or the depth of 2 meter under the corner of the rectangular region will have the stress increase by 22.3 kilopascal. Right? That's going to be same as here and the other corner. Right? And the next one, find the vertical stress increment sigma z by the loading under the center of the footing at a depth of 2 meter. So now it's the same geometry and the Q is still the 100 kilopascal. And then now we're looking at the under the center of the footing area. Then now if you look at from the top, this is 3 meter and this is 4 meter. What we are looking at here, so we can divide this rectangular region into 4 rectangles. So now the x is 1.5 meter, and y is 2 meter, and z is still 2 meter. So then m is 0.75 and n is 1. And using that, if we go back to this chart, then n is 1 and 0.75 is somewhere here. So it's gonna be 0.15, more than 0.15, so 0.157. So sigma z will be q naught times I. This is rectangular ABCD times 4, so 100 times 0.157 times 4, that gives you about 62.8 kilopascal. So if you compare the one at the top here, at the corner you have a 20.2, here you have about 62 kilopascal, 63 kilopascal. Right? So then that means that when you look at from the section view at the surface, and the loading area is here, this is 3 meter, or the 4 meter is okay still, 4 meter. At the center, when it's 2 meter, here is 62 or 63 kilopascal if you round up. At the corner, but it's still the same depth, it's 22 kilopascal. So it shows that as the radial distance increases, the stress will decrease like this, huh? Or it could be like this, more of. Good. Okay, next one. Find out the vertical stress increase outside the loaded area. Yeah, so even though this location is outside this footing area, the soil may feel the stress increase. Then can we get one? In theory, yes. So if we use in the Newmark solution and just the same rule, we can get the sigma z at the location here, outside of loading area. If you look at from the top, this is the loaded area, right? And you can also draw a rectangle that that passes the point of interest E here. This is the point E. And then you can divide this rectangular area into big two rectangles. So then we have this rectangle I B A E D B A E D, right? That's passing this the point E, and then if we subtract this rectangle, that's C F E D, then this becomes the influence factor for the E. So then delta sigma Z at E will be Q naught times I B A E D minus I C F E D times 2, because we are looking at only this one. So this is going to be the influence factor actually for this circle. Okay, so then using the Newmark solution, you can get this one, right? Because you know the x and y and the z is given. And for the CFED also, you know the geometry, x and y and the z. So then you can get the I, the influence factor, and then you can compute the stress increment outside the loaded area. Right? Okay. That's all for this lecture 23. Thank you.